Okay, so let's take a look at problem number 1. It says, let f be a function whose graph is given. Estimate the value of f of 2. So be careful, where is your x and y axis, so you don't end up counting wonky. And if we look at f of 2, it looks to be roughly here, which to me is probably about 2.7. Now, if you said 2.6 or 2.8, roughly 2.7. It says estimate the value of x when f of x equals 3. Remember, we're looking for a height of 3. Now, there are 2 values you should be giving me where there is a height of 3. So give me the x value where that happens. So this one looks to be about 2.2. And the other x value seems to be 5.5. Now, we're going to assume that this function does not keep going. They didn't put arrows to assume that. I will put an arrow on the end if I assume this function keeps going on and on and on, okay? But the domain then looks like it is going to be the x values from -6 to +6, and put those in brackets. The range, our lowest value appears to be -5. Our highest value appears to be positive, or is that 4? Wait, 1, 2, 3, yeah. Appears to be -4 and +4 and everything in between. So our range goes from -4 to +4. On what interval is function f increasing? So if we look at an x value right here and an x value right there, those are our turning points, our changes in increasing to decreasing. So the only place it's increasing is this middle portion of our function. So you have to tell me the x values where that happens. So it's increasing on an x value of -4 to an x value of +4. Now, it's not customary to put brackets on there because those switchover points, those turning points, they don't include, because one side you're increasing, one side you're decreasing. What are you doing? So they don't include them. So it's customary for increasing and decreasing. Don't use anything but a parenthesis. This function, based upon the fact that it is so perfectly symmetrical about the origin, meaning this point and those point go together, and this point and this point go together, and this point and this point go together, and so on. And you could put a push pin here and you could rotate it like a pinwheel. So from the explanation, I just, and you don't really have to explain too much, but it's odd and it has origin symmetry, would be, I guess, a good explanation. Do we have any questions about number 1? Good? Makes sense? Maybe? Okay. It is a very ugly bracket. Okay. Anything else about number 1? Okay. Number 2 says determine whether each curve of the graph is a function of x. If you take a look at this one, what happens right there? A vertical line hits it how many times? Multiple, right? 4 times, it looks like. So this one's a no. Remember, a vertical line can only hit a function in one place. Any vertical line you draw could only hit it in one place. But if we look at this one, bam, 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 it's perfectly fine. So this one's a function. And then they said, what's the domain and range? Our lowest value of x is -3 and it has a closed-in dot, and then +3 and it has a closed-in dot. Our range, since they didn't leave their pencil up at all, it's continuous, and its lowest value appears, and you're just going to have to guesstimate, and I'll understand that, to go to -2. Its highest value appears to go to +3. And then it would be all the values in between. Okay. Everybody good with those? Okay. The vertical lines, all vertical lines only ever hit it once. Yes. This one failed because there's this section here in the middle where there's like a backwards, it slides backwards. Now 3, you guys, many of you missed this question on the quiz. So let's talk about this one. So what I would do if I were the student taking this is I would calculate A plus H. I would calculate A, and then I would put them in the correct location in the formula. So that's probably the best way to handle that part of things. If you plug in A plus H, that's A plus H squared minus 2 times A plus H plus 3. Now, I expect, because we want to complete the difference quotient by dividing off the H, you have to multiply all that junk out. So we get A squared plus 2AH plus H squared minus 2A minus 2H plus 3. There are no like terms. It is what it is. And then if we plug in A, that's just an easy A squared minus 2A plus 3. Replace your X's with your A's. Now, once we have those done, we're going to just plop them into the formula. And now here's, when you plop them into the formula, my suggestion to you. So if we put the A plus H in, that one's easy. We just plop it in. And that was the beauty of getting it done sooner. But when you plop in the f of A, please put it in parentheses so you remember to distribute to all the pieces. If not, you'll mess that up. So that's A squared minus 2A minus 3 all over H. So that's what we get initially. Now, what's nice about that is the fact, remember, once you distribute this, everything that does not contain an H should have an opposite in the problem and cancel out. So we get A squared plus 2AH plus H squared minus 2A minus 2H plus 3 minus A squared plus 2A plus 3 all over H. And then just start canceling things out, okay? This doesn't have an H in it. Its opposite should be laying in the problem somewhere. There's nothing for the 2AH. There's nothing for the H squared. But negative 2A has an opposite, positive 2A. Negative 2H is fine. And then finally, we have a positive 3 and a negative 3. Let's see. Oh, because I wrote something wrong, didn't I? That's a plus. That's a plus. So that will be a minus. I mean, that's one thing about these. They always should cancel. If they don't, like I just did, I made a mistake. I wrote something wrong. I had it here correct, but then I wrote it there incorrect. Okay. So now we have those things canceling. Rewrite the things that are left. They should all contain H's. They should all be divisible by H, or you did something wrong. So divide everything through by H. We're left with 2A plus H minus 2. Okay. So that is the difference quotient. Do we have any questions about that? We will be using the difference quotient as we start the next chapter. So please make sure that you understand how that works, because that's not going anywhere. Thank you. Okay. So let's talk about domains. Let's jump to 5 through 8. Okay. Let's get the easy ones out of the way. Let's get 7 and 8 out of the way. The domain of a sine and cosine are all real numbers. We can plug in anything we want, nothing messes it up. The inner function, in one case an x, in the other case a 2t, those are also functions that domain are all real numbers. So the domain of both of these are all real numbers. And you can put the all real symbol, or you can put negative infinity to positive infinity, that's fine too. But what I want to talk about more thoroughly is 5 and 6. Hopefully you remember that the thing that messes up a fraction is the denominator is not allowed to equal 0. What messes up a square root is you can't plug in negatives. So those are the things you keep in mind when you look at something like that. So let's address number 5. And I don't think I'm going to be asking range at this time. But how would you do range? You just need a picture. So unless I have you graph it, I probably won't ask for range. Okay, anyway, let's look at 5. So the problem with that fraction is you can't have a denominator that's 0. So just take that denominator, set it equal to 0. Let's find the value that messes it up. Well, that hopefully you don't question that 1/3 causes that issue. So just a little slash through it. Now, I want your answer in interval notation. This function works everywhere except 1/3. There's actually an asymptote there. It basically looks like this. At 1/3, there's an asymptote, and I believe it looks something like that. But it has 2 pieces. So our interval notation should look the same. It should have 2 pieces. And so our domain would go from negative infinity until it hit that asymptote on the left side. It will jump across that 1/3 gap, and then it'll keep going forever and ever and ever. So you'll notice that we have skipped 1/3. And that's how we denote that, using parentheses. Don't use a bracket. That means we landed at 1/3. We don't land at 1/3. We skipped it. Now, the problem with a square root is the inside has to be greater than or equal to 0. Now, last year, I believe, I don't remember when, we had done some things with the plus minus charts with our inequalities, okay? Plus minus charts are your key here. Let's factor that into pieces. That would be 4 minus x squared, 4 plus x squared. 4 plus x squared is not factorable further. That is a prime factorization. That's as far as you can go. But 4 minus x squared can reduce to be 2 minus x and 2 plus x. So break it down as far as you can. Break it down as far as you can. And then what we're going to do from there is we are going to make the plus minus chart. Okay. So how do we do that? Well, we think about making it a number line as a placeholder. This equals 0 at positive 2. This equals 0 at negative 2. This does not equal 0. So the only values I got to put on there are negative 2 and positive 2. Now, I'm allowed to equal 0, so color those in. And then along the edge, either left edge or right, it doesn't matter. Let's put down our factors. 2 minus x, 2 plus x, and 4 plus x squared. Now, you might recall This is the one where we did test values. Think about just numbers on the number line in that section or that interval. So let's just go -3, 0, and +3 as our testers. Now we're going to plug those into each of those. All we have to record in our chart is the plus or minus. That's why we call it the plus or minus chart. Isn't that amazing? If we plug -3 into the top, we get +5. If we plug -3 into the middle, we get -1. If we plug -3 because we have to square it, it becomes 4 plus 9, which is a positive. Plug in 0, we get +2, +2, and +4. Let's plug in 3. If we plug in 3, we get a negative, we get a positive, we get a positive. And so then now let's determine what the intervals are. This interval here is negative, positive, negative. We only want the greater than or equal to 0. We want the positives. We only want the greater than or equal to 0, so we want the positives. So let's color those in, or it in. There's only one of them. Let's color that in. That's the domain of this function. The domain goes from -2 to +2. If you graph 16 minus x to the fourth, if you graph 16 minus x to the fourth, it would start at a height of 16. It would look like a parabola going downward. It hit the x-axis at +2 and -2. The only thing then that's positive is the x values between +2 and -2. So the graph also can help answer this question. But that would be the domain. So here's the key takeaways. To find the domain of a fraction, set the bottom equal to 0, discard that value. There might be 1, there might be multiple. 6, 1 like 6. If you were doing a square root, it has to be, or an even index, like a 4th root, a 6th root, an 8th root. The thing inside has to be greater than or equal to 0. Almost everything else, the domain's all real numbers. Now, I'm not going to throw tangents, cotangents, secants, and cosecants at you, because those are a little bit wonky. So I won't do that on the test. But you have to keep that in mind as well, okay? Yeah. Yes. So there's 5 and 6. Okay. Let's keep going. Let's talk about 9. Yeah. I can look. We can look. We can figure that out. Okay, let's take a look at 9. 9 says describe how the function has been transformed from f. So we're just gonna write a little explanation. So what happens when we add that 8 on the outside of the function? Yep, so all you have to do is say update. What about if we add 8 on the inside of the function? Opposite of what you think. If we add 8 on the inside, it's going to go left 8. Serenity. Who was the other one? Dan. Let's take a look at C. Now, follow order of operations in your description. What hits the F first? What hits the F first? The 2, right? That's going to stretch it by a multiple of 2. It's going to change the distance by a multiple of 2 from the x-axis. So I would say it's going to double the height. Once you've doubled the height, what's the plus 1 going to do? Maybe go up 1. And you can rearrange it. If you like it to say 2f of x plus 1, go for it. Stretch 2 is fine. Yep. And then let's look at D. Follow order of operations. What's the first thing that happens? Right 2. And then what's the next thing that happens? Down 2. E, what happens to that? Flips it over the x-axis. Yes. When there's a negative on the front, it flips it over the x-axis. If there's a negative on the x, it flips it over the y-axis. Now, F, follow order of operations. What did we say in E? What did the negative in front of our F do? It flips it over the x-axis. But we have a 3 there. So this is a perfect one where I like the rewrite you were suggesting before. Let's rewrite that as negative f of x plus 3. So we can see that that 3 is positive and how it's affecting us. If we follow order of operations, the first thing that touches the function is that negative. We know that flips it over the x. Yes, just a second. Let's flip it over the x-axis. And then that 3 now, as we can see clearly, it's an addition of 3, a positive 3. It's going to go up 3. If we had it like that, that flips it over the y-axis. That's why in an even function, it doesn't do anything, because it'll just flip it back and forth and it won't change it. You know, like x squared, if we plug in negative x, you get x squared. And that happens for our even functions. Okay. 17. Hopefully you know how to do even, odd, or neither. If you plug in negative x to this one, the first piece changed, but the middle or the last 2 pieces do not. So it's nothing good. It's neither. Here, when you plug in negative x, it is like I multiplied through by negative 1. It's odd. Here, if you plug in negative x, it does nothing because that negative squared gets to it. So it goes right back to the original. It's even. Of our trig functions, cosine is even. Sine is odd. So normally I would say that this one is odd, but an odd function has to go through the origin. You can't have a piece that's odd and a piece that's even. Like these ones up here, that's an odd term. These are even terms. That's why it's neither one or the other. Same thing kind of happened here. An odd function has to go through the origin. This goes through 1. And so this is neither as well. So kind of a weird one. But I will ask you about that. I'm not super concerned about the trig functions. Make sure you know how to do it for a polynomial. Something simple. No, I mean, if you really just look at the functions, the way that the cosine is drawn, it is even. The way that the sine is drawn, it goes to the origin, it's odd. Okay. Please, let's go to graph 23 here. Here we're going to talk about some limit stuff. So remember, day 2 of the test is about limits. Okay, so the first thing they say here is find each limit or explain why it doesn't exist. There might be a few that I might talk about a little bit more thoroughly. So one says we're coming in to an x value of 2 from the right. That's what that little plus notation means. So find your x value of 2, that's this one. Coming in from the right, we are heading to a height of 3. Now, if they ask the limit as x approaches 2 from the left, oh, that's this one. That's this one right here. This one. So if they come into an x value of 2 from the left, what happens for that side? It's an asymptote. It's going to keep sliding down there. So that would be negative infinity. So if they said without any notation, they just said what is the limit at 2, we would say it does not exist because of the fact one side's one thing, one side's another, they don't match up, they're all funky. Okay. Now let's do the -3 stuff. In 2, they say approach -3 from the right. So what height are we getting toward? 0. Now let's do the limit as we approach -3 from the left, because they didn't ask us that. So if we approach it from the left, what height are we going toward there? -2. So when you get to answer question 3, one side we found was going to 0, the other side we found was going to -2. That's a perfect example where that discontinuity happens. That's a jump discontinuity. It doesn't exist. X equals 4's limit. 1, 2, 3, 4. So we're looking at what's our height coming in from the left and the right. It is at a height of 2. So the limit is 2. See how we have to lift our pencil to make the dot that's here? So that is a discontinuity. The limit exists, but the function value isn't 2, it's 1. So when the function value and the limit don't match up, that's a perfect example where we would say that there's a discontinuity. Now let's talk about vertical asymptotes. The only vertical asymptote is at 2. So that's always an x equals number. Oh, yeah, it's 0. Sorry, this one is 0. I wasn't even looking right there. Yeah, okay, so there's a vertical asymptote here, and there's a vertical asymptote there. Wonder why the faces. Is there another one? Yes. Doesn't matter. It's still considered a vertical asymptote on the left side. So we need a vertical asymptote there to account for the fact it's not a vertical asymptote in the sense of what we normally think of one. We think that as being an undefined value because of the fact that this is such a bizarre piecewise function. It is defined at that point, but there would still be a vertical asymptote that this side is approaching. So even if you kind of keep it down there, that's okay. Okay. So where is there a jump, a hole, or a vertical asymptote? That would be the numbers where f is discontinuous. We're going to find vertical asymptotes, and discontinuity is going to be there too. Okay, so the x's we have to account for are -3, 0, 2, and also 4. So there's a jump here. That's your x equals -3. There's an asymptote here. There's a asymptote weird disconnect there, and there's a disconnect there. So there are 4 spots in the graph that are messed up. So these are the discontinuities in the graph. So, oh, I did not do that one. Let's do that one. Oh, so they're both going up to infinity. So that is one where we can get an infinite answer. Positive infinity would be for 5. Yes. And your vertical asymptote, they both are heading upward. So for you to get an infinite answer or a negative infinite answer, they both have to be going swooping up or swooping down next to it. Otherwise, we say it doesn't exist at that spot. Yeah, because they both are going in the same direction. That's just kind of a notational thing. Yeah, there's nothing there. But on each side, we're heading to the same place. So we're both going to infinity in that case. Everybody go with 23. Okay. Let's talk about some limits of actual functions, okay? So now I want to focus on, and probably for the remainder of class, just this section right here. So first, I'm going to do the odd ones to start with, and then if we have time, we'll come back to the evens if we have time. Okay. So my first suggestion, anytime they ask you to calculate a limit, you always try direct substitution. Just try direct substitution, see what happens. So this is the cosine of 0 plus the sine of 0. And we always assume in calculus class that they're talking about radians. Okay. So what is the sine of 0? What is the sine of 0? 0. It goes through the origin. It's 0, 0. The height at 0 is 0, however you want to think about it. So this would just be the cosine of 0. Cosine is a continuous function. We never have to leave our pencil. We have to lift our pencil. It's a perfect little wave. So the cosine of 0 is defined. Anybody remember what the cosine of 0 was? 1, right? It's over at 1. Your unit circle. So the answer is 1. Let's plug in 27. Let's plug in -3. We get -3 squared, which is 9. We get 9 minus 9 on top. On the bottom, we get 9 minus 6 minus 3, or we get 0 over 0. That indicates there is a hole in the graph, but the limit probably exists. So it is your job, when this case happens, it is your job to manipulate the algebra and fix the problem. For polynomial over polynomial, the algebra can be fixed just by factoring. There's a factor on top and a factor on bottom. If it's -3, the factor is probably an x plus 3 is causing the issue. So if we factor the top, hey, guess what? X plus 3 is in there. If we factor the bottom, we get x plus 3 and x minus 1. So you would cancel out the matching factor. We would use the x approaches -3 on this reduced function. And so we just plug -3 now. We get to use direct substitution again. And that's always the technique you try anyway. If you plug in -3, you get -6 over -4 or 3/2. Bam, we're done. 29, try direct substitution. If you plug in 0, you get 0 over 0. There's a hole in the graph. Let's plug the hole. Let's figure out where that hole is. So if you cube that, I'm going to give you just the solution right now. H minus 1 cubed is h cubed minus 3h squared plus 3h minus 1. And then we have that plus 1 there all over h. Does that look familiar to you? The difference quotient should always cancel and reduce. That's what's going to happen here. The 1's cancel out. Now everything is divisible by h. We're going to take the limit as h approaches 0 of the reduced version, h squared minus 3h plus 3. And then the answer is 3. Okay. Let's talk about 31. First thing we try is direct substitution. We get 3 over 0. There's not a hole in the graph there. There's a vertical asymptote. So remember, this means hole. You can manipulate the algebra and fix it. This means vertical asymptote. You can't fix it. Instead, what we do is this is the one where we're going to plug in a 10 above and a 10 below. If they give us a positive number both times, it's positive infinity. If they give us a negative number both times, it's negative infinity. If one's positive, one's negative, it's swooping in the wrong direction. There is no answer. Okay? Okay. So we're going to do direct substitution. I'm just going to call this f of r, just so I have something so I can show you. Okay. I'm going to plug in 8.9. I'm going to plug in 9.1. I usually do a tenth away. That's usually close enough Some books will show you 100th or 1,000th. I've always gotten the answer a tenth away, so that should work for us. If you plug in the square root of, or if I plug in 8.9, all you got to do is think about positives or negatives, kind of like a plus minus chart. You don't have to get an actual numerical value. If I plug in 8.9, I get a positive on top over a negative number to the fourth power, still positive. I get that the left side is going to positive infinity. If I plug in 9.1, same thing happens. I get a positive over a positive. I get positive infinity. That is our answer. If the sides don't match, the answer does not exist. They might be, if they put a negative right in front of the square root set of r, then the answer would have been negative infinity. So just be careful and do that. Yeah. Okay. 33 is very much like 27. That is a factorable quantity, so I'm going to assume you know how to factor. I want to talk about 35. We try direct substitution. We get 0 over 0. There's a hole in the graph that we need to plug. Let me show you how to plug a square root one. Surround your top and bottom by parentheses. That is an S, by the way. Multiply top and bottom by the conjugate of the square root piece. The conjugate of the square root piece. I hate making an S. It doesn't look like an S. I apologize. Okay. The bottoms don't actually do anything with it. There's a 0 denominator I want to get rid of anyway. So the bottoms, 99% of the time, unless my square root was in the bottom, I don't multiply the bottoms. It's going to waste my time because I'm just going to have to factor it anyway. So leave the bottoms. The only math we have to do is on the top. Well, what's great about conjugates is their difference of squares. So if I square 4, I get 16. If I square a square root, the square root pops off. So I get 16 minus s. Now, 16 minus s and s minus 16 are opposites. They can cancel out. You can cancel out a subtraction that is switched as long as you leave a negative one behind. Now, why does that happen? Well, we could rewrite the top like this. I could factor out the negative if I wanted. That's why they cancel and leave a negative one behind. It will switch the subtraction. So if you have an addition that's switched, like s plus 16 and 16 plus s, they're the same thing. But if you have a subtraction that's switched, they're opposites. In one, the s is positive, the other, the s is negative. In one, the 16 is negative, and the other, the 16 is positive. So it just, if you can cancel that out, leave a negative one behind. So now we're going to take the limit as s approaches 16 of negative 1 over 4 plus the square root of s. Well, the square root of 16 is 4. 4 plus 4 is 8. The answer is negative 1/8. So you can always fix a 0 over 0 case, a hole in the graph, and find the simplified version. If there is a square root, use the conjugate. If there is a square root, use the conjugate. So I hope that helps you with those. Oh, let's do one more before we say goodbye. Intermediate value theorem. It says use the intermediate value theorem to show that there is a root of the graph. All you got to do for 49, please don't make these hard. There's such a great problem because you can say our function is continuous. We'll call this our function. Why do we know it's continuous? It's a polynomial. It's just some bumps, a squiggly, bumpy thing, okay? If you plug in 1, we're going to plug in the endpoints. If we plug in 1, we get 1 minus 1 plus 3 minus 5 is negative 2. If we plug in 2, we get 32 minus 8 plus 6 minus 5, which is 25. There must be a 0 in here, because if I was at a height of -2 and now I've come up to a height of 25, it's a continuous function. I never have to lift my pencil. There's a 0 in there, right? That's all that says. If one side is positive and one side is negative for a continuous function, you had to cross over 0. There's a 0 in there. Do I care where it's at? No. It just is there. Okay. So that's kind of what your test is going to look like. I would review this. I'll post this video. I would suggest reviewing the one that you were supposed to watch yesterday. Please turn this in at this time. Is there a second review day? Is there a place to put it? Okay, I'll make a place. So there you go.